welcome. In Chapter 5, we discussed a chemical equation, the concept of a mole, and also the concentration of solutions. In Chapter 6, we're going to go through some new concepts which include gases, liquids, and solids, or the states of matter, as well as intermolecular forces. The three most common states in which matter can exist are solids, liquids, and gases. There is a fourth state, which is called plasma, that we will briefly mention, but these are the three main states of matter that you need to be accountable for in this course. We'll begin with the solid. A solid has the particles in fixed positions and exhibit motions of vibration. Now, every molecule is constantly moving and vibrating. The bonds between atoms within the molecule are expanding and contracting back and forth at rapid motion. In a solid, the space between the atoms is the smallest. The atoms are the closest together, and they have fixed positions. As the amount of energy between the molecules increases, the movement and vibrations also increases at a rate, and eventually the particles expand away from each other. This is when a material can enter the liquid state. In a liquid state, the particles are free to move within the confines of the liquid. And then finally, when the individual molecules have the largest amount of energy, they enter the gas state. Here, the molecules are moving far apart and in random directions. Substances can go from one state of matter to another state of matter, and these state changes each have their own unique phrasing. For example, a melting point is the temperature at which a solid transitions to become a liquid. Vaporization is the process from which a liquid becomes a gas, and the boiling point is the temperature at which a particle of a liquid escapes to become a gas. Notice the difference between vaporization and boiling point. The process of a liquid becoming a gas is vaporization, whereas the temperature at which this process occurs is the boiling point. Condensation is the process by which a gas becomes a liquid. You might be familiar with condensation of water on a foggy day on the windshield of a car. The process by which a liquid transitions to a solid is called freezing, and this is going to occur at the freezing point. The freezing point and the melting point are exactly the same. A substance can freeze or melt and go back and forth between these two states of matter at the freezing point. And then finally, a state change which you are likely less familiar with is sublimation. This is the state change when a solid changes directly into a gas and completely skips the liquid state. If you recall, we talked about the amount of energy contained in a sample causing the bonds to move and vibrate at a higher rate. This is a direct relationship to the state changes. On the x-axis of this graph, we have the energy content of the sample, and on the y-axis we have the temperature. As we increase the energy content of the sample, the temperature also increases, right? As we increase the temperature of the sample, the energy content increases. As the energy content increases, the amount of energy within those bonds and the rate of their vibration and movement increases, and they expand further and further apart. We can start here at the bottom. This is the lowest temperature. As we take a solid and warm it up along this red line, eventually we'll hit the melting point. This is where the solid will begin to transition into a liquid. At this point, the temperature will remain the same of the molecules within the solution until they fully have melted into a liquid. Once they hit the fully melted portion, then the temperature will continue to increase as the liquid warms up, and eventually it will hit a new temperature, which is the boiling point. And at this point, the liquid will begin to vaporize into a gas. That was a brief introduction of the states of matter. Now we'll talk about the intermolecular forces and how they relate to the states of matter, how these forces hold the molecules together. The first bond we'll talk about is the ionic bond. We've already gone through the chemical rationale behind the ionic bond. The ionic bond are the strongest forces that can hold matter in the condensed states. The bond between a sodium and a chlorine is going to be the strongest type of intermolecular force. The ionic bonds are the strongest intermolecular forces. The rest of the intermolecular forces that we will look at are going to be weaker than the ionic bonds. Polar molecules exist as dipoles, and these dipoles have intermolecular forces. The positive end of one molecule is going to be attracted to the negative end of another molecule. And so the molecules will line up in a polarized fashion with the negatives being attracted to the positives. This intermolecular force will pull the molecules closer together with attraction. A hydrogen bond is most commonly found in water, but it's also contained in any molecule that has an electronegative atom attached to hydrogen. A hydrogen bond is a fairly weak intermolecular force, but when there's a large amount of them occurring, they can add up in strength over time. When a hydrogen atom is covalently bound to a highly electronegative atom, most commonly nitrogen and oxygen, it can exhibit an additional polar attraction. You can see in this example we have a variety of different water molecules, and the lone pairs on one oxygen are going to be attracted to the hydrogen of a different molecule. So each water molecule has two lone pairs and it has two hydrogens, meaning it can participate in a total of 4 hydrogen bonds. The last intermolecular force that we'll introduce is the dispersion force. This is a force that occurs between fairly nonpolar molecules. And the strength of this force is going to be directly correlated to the molecular weight, or how large the molecule is. This is also known as London dispersion forces. To begin with, the electrons will be evenly distributed between the two molecules. Over time, there will be a state where the electrons in the left molecule are momentarily clustered to the left, and this will create a momentary dipole. When this occurs, the dipole will then attract the electrons in the molecule to the right, and will end up with a stacking effect of these forces over time.